Welcome to Lecture 3 of Circuits 1. First little while in this lecture we're going to review Ohm's law, power, and power conservation, just to make sure that those are fresh in our mind. The bulk of the lecture will be spent talking about two analysis techniques for circuit analysis, Kirchoff's current law and Kirchoff's voltage law. As I've been mentioning when I was talking about the passive sign convention, we need to use the passive sign convention correctly in order to make our later analyses turn out right. It's now time to start doing some of those analyses and seeing the effect of the passive sign convention. Related written educational material is in section 1.4 of the educational modules. Real quick review on Ohm's law. If I have some resistor denoted with a resistance R, and I have an assumed voltage drop across that resistor, the relationship between the current through the resistor and this voltage is given by Ohm's law. The voltage is the resistance times the current. Now, in order for this relationship to be valid, we have to obey our passive sign convention. Positive current has to be assumed to be going into the positive voltage node. That's kind of analogous to the case of a dynamics problem, for example. If I have some mass that has some position x, and if I'm interested in the velocity of that mass, I can determine the velocity by the rate of change of position with time. Velocity is dx dt. That assumes, however, that velocity is positive in the same direction that x is positive. If I assume that velocity is positive to the left, I need to invoke a negative sign here and change this relationship. Likewise, if I want to assume anything other than my passive sign convention for voltage versus current, I need to change this relationship, which I don't want to do, so I'm always going to stick with the passive sign convention. Power. The power absorbed or generated by an electrical circuit is given by the product of voltage and current through the circuit element that we're interested in. Now, we have to be worried about whether a particular circuit element is absorbing or generating power. If this power is positive, the circuit element is absorbing energy. If this is positive, I and V agree with the passive sign convention. They are either both positive relative to the passive sign convention or they're both negative relative to the passive sign convention. For example, if I have some circuit element here with a voltage difference across it and a current going into it, where I've defined my positive voltage polarity as shown and current is going into the positive voltage node, and say I do my analysis and I find out that V is 3 volts and I is 1 amp, okay, then power is 3 volts times 1 amp, or 3 watts. Since this is a positive number, that indicates that power is being absorbed by this element. That means that I and V agree with the passive sign convention. If I do my analysis and find out that voltage is, for example, minus 2 volts and the current is minus 3 amps, power is still the product of voltage and current, so I have a minus 2 volts times a minus 3 amps, which is a plus 6 watts. That simply means that the voltage polarity is the opposite of my sign convention, and the current direction is also inverted. So I really have 2 volts this direction, and I have positive 3 amps into that node. This still agrees with the passive sign convention. The element is still absorbing power. If the element is generating power, the power is going to turn out to be negative. That happens if I or V individually have an opposite sign relative to the passive sign convention. If current is going into the negative voltage node, power is generated. So for example, our similar example as before, if I have assigned voltage being positive polarity this way and currents assumed direction being positive that way, if I find out that voltage is minus 2 volts and current is plus 3 amps, then power is minus 2 volts times positive 3 amps is minus 6 watts. This element is generating power. Because the voltage polarity is plus minus 2 volts, I is going in the direction I've indicated here, which is 3 amps. Current is actually going into the negative voltage node, so power is being generated. We also talked about conservation of energy during the last lecture. Within an electrical circuit, the amount of energy generated in that circuit has to balance out with the amount of energy absorbed. So if we sum up the power contribution from all elements, we have to end up with 0 for an overall electric circuit. This summation works because power absorbed is positive, power generated is negative. You can cancel out the positive and negative contributions and end up with 0. Okay, today we're finally getting into some new material. We're going to talk about Kirchoff's current law and Kirchoff's voltage law today. These are our main two analysis techniques. This is basically how we're going to be writing governing equations for electrical circuits for the next semester or the next 2 semesters or probably the rest of your college career. Now, in order to understand Kirchoff's current law and Kirchoff's voltage law, we need to generate some basic definitions first. These laws will be defined in terms of nodes and loops in an electrical circuit. Our definition of a node is going to be that a node is a point which connects 2 or more electrical circuit elements. For example, in this particular circuit here, we have a voltage source which is connected with a resistor. This point of connection is a node. I'm just going to call that node 1. Right here, we have connected a current source with a resistor. This point of connection is also a node. Call that node 2. There is a little bit of a subtlety here. We have some other potential nodes here. A, B, and C are all connecting stuff up. D, E, F, and G are all connecting stuff up. A single node can actually be spread out by perfect conductors. If I do not put a circuit element in my circuit schematic, I assume that there is no resistance between those 2 points. That means that node A and node B are at the same voltage by definition. Likewise, node B and node C are at the same voltage by definition, which means that all 3 of these nodes share a common voltage. So a node has a single voltage. So this whole setup here is a single node. These 4 points which appear to be separated on this schematic are also a single node. So just because they look separated physically doesn't mean that they are electrically isolated from one another or are electrically different in any way. Okay, a loop in an electrical circuit is any closed path in a circuit which encounters no node more than once. By closed path, the main thing that's important here is that we have to end up at the same node that we started with. So for example, in this circuit here, we have a number of possible loops. We can generate a loop that goes through D, A, B, E, and back to D. We can also have a loop which goes through E, B, C, F, and E. This loop here goes through F, C, and then back to G. We can also generate loops in here. So this loop here, I've started at A, B, C, F, E, D, and back to A. This loop here B, C, G, F, E, and back to B. I also have one additional loop. I can go around the entire outer perimeter of this circuit. Okay? So we have 1, 2, 3, 4, 5, 6 loops in this particular circuit. Kirchoff's current law states that the algebraic sum of all currents entering or leaving any node has to be 0. For example, if I have some node here and I have a bunch of currents that are all defined as positive going out of that node, if I add up all those currents, they have to sum to 0. An alternate statement of Kirchoff's current law is that the sum of the currents entering a node has to be equivalent to the sum of the currents leaving the node. For this particular case, mathematically, if I do a sum from k equals 1 to n of I sub k, so I1 plus I2 plus I3 on up to I sub n, if I add all those up, I have to get 0. Now, obviously, since all of these are defined positive as going out of the node, some of these currents actually have to be negative. So if this is a negative number, it simply means that that current direction has switched. It's going into the node rather than out of the node. All Kirchoff's current law is telling us physically is really that we can't accumulate charge at a node. Okay? We have to take away as many electrons from this node as we're putting into this node. A couple things about Kirchoff's current law. In order to apply this, the current directions entering or leaving your node are based on the assumed directions of the currents. Remember, in the passive sign convention, we have to assume a current direction. This is intimately tied up with that assumption. We also need to decide whether we want to think of currents entering the node as being positive or whether we want to think of them as being negative. Either way is fine. We just have to decide what we're going to do and be consistent about that. As long as we're consistent with all these assumptions, when we get our final result, we know how to interpret a negative sign in our currents, because that will reflect a change in direction from what we assumed. If the resulting current is positive, it means that we've assumed the correct direction. Okay, quick example. Try this one out. Come back and watch me do it. Okay, I want to write KCL for this particular node. I have I1 of t, which is assumed to be going into the node. I have I2 of t, which is assumed to be going into the node. And I have I3 of t, which is assumed to be going out of the node. I have to decide which of these I want to be positive and which I want to be negative. I think just for kicks, I will assume currents entering the node are positive. Okay. If I assume that currents entering the node are positive, then I add I1 of t. So this I2 of t is a positive current. And then I add I3 of t. It's leaving the node. So I actually end up subtracting that one off. These have to sum up to be 0. Okay, so I end up with I1 of t plus I2 of t minus I3 of t is equal to 0. You don't like that assumption? Okay, change it. I'm going to keep my previous result up there just for kicks. Let me assume that currents leaving the node are positive. If I do that, this current becomes negative. I have a minus I1 of t. This becomes a negative current because it is actually entering the node, minus I2 of t. This one's leaving the node. It will be assumed to be positive, plus I3 of t. That sums to 0. If I take this guy here, multiply it by -1, I get this result They're both identical. I've just consistently changed my signs throughout. Another example of Kirchhoff's current law. I have some currents here, some of which I know, one of which I don't know. I want to use KCL to determine what this current is at this particular node. Okay? Make an assumption as to whether the currents entering the node are positive or whether the currents leaving the node are positive. Let's assume, I don't know, currents leaving the node are positive. I have 4 amps coming into this node. It is going into the node. I actually treat that as a negative 4 amps because only currents leaving the node are positive. This current is leaving the node, so this is a positive current, but it's actually a positive negative 1 amps. If you want to, change the direction and call this positive 1 amp, you will get a negative 1 amp leaving the node. This guy here is leaving the node, it's purely positive, plus 2 amps. I is assumed to be leaving the node, so it is an additive element. So minus 4 minus 1, minus 4 minus 1 is minus 5, plus 2 is minus 3 amps, plus I is equal to 0, so I is equal to 3 amps, and it is actually 3 amps leaving the node, so I don't have to adjust the direction on that particular current. Okay, now we're going to talk about Kirchhoff's voltage law. Kirchhoff's voltage law states that if we go around a closed loop in a circuit, the sum of the voltage differences around that closed loop must be 0. For example, if I have some closed loop in a circuit with some circuit elements around it, if I go around this, keeping track of the voltage differences, V1, V2, V3, on up to V sub n, there are probably a number of other circuit elements in here. If I add up all those voltage differences, I have to get 0. Okay, that implies that some of these voltage differences are going to be rises, some of them are going to be drops. They have to balance out. So another way to state Kirchhoff's voltage law is that the sum of the voltage rises around a closed loop has to be equal to the sum of the voltage drops around the loop. Mathematically, for this particular case with n elements in the loop, if I add up all the voltage differences here, I'm going to end up with 0. Some of those voltage differences will be positive, some of them will be negative. Physically, all Kirchhoff's voltage law is telling us that if we go around a loop, we have to end up with the same voltage that we started with. So if I start here and add up all the voltage differences until I get around to here, I better come up with 0 because this guy here has only one unique voltage value associated with it. Couple of items or hints about applying Kirchhoff's voltage law. Again, you have to be consistent with your assumption. The voltage polarities are based on the assumed polarities that you assign. Those have to be assigned according to the passive sign convention. As long as these are consistent, your final result will reflect the actual sign of the voltage polarity. So if you get a negative voltage, that simply means that you've assigned the wrong voltage polarity to that particular voltage difference. In order to make sure that this is consistent, I recommend a fairly rigid approach toward this. On your circuit diagram, indicate all of your voltage polarities, the assumed polarities. You don't know what the actual polarities are going to be until you're done analyzing the circuit. Indicate the loop that you're taking and the direction that you're going around that loop. The direction doesn't matter. Keeping track of what the direction is does matter. As you follow the loop around, on your assumed polarities, if you encounter a plus sign first, treat that voltage difference as positive. If you encounter a negative sign first, treat that voltage difference as being negative. If you want to do exactly the opposite of this, that's fine with me. As long as you're consistent about what you do, you should end up with the same result. Okay, I have an example for you. I want you to apply KVL to the 3 loops in this circuit using the assumed voltage polarity that I gave you. So I have one loop here, and one loop around the entire perimeter. So try that problem, come back. You can watch me do it in a couple of minutes. Okay, I'm going to call this one loop 1. Okay. Doesn't matter where you start on this loop as long as you end up at the same point that you started at. For some reason, I tend to start out at the lower left-hand corner of my loops. I really have no idea why. So I'm going to start at point D, and I'm going to work my way this direction clockwise around the loop. So if I start applying KVL around loop 1, I hit V3. If I'm coming this direction, I see a negative sign first. That means I'm going to treat V3 as a negative voltage. Coming around through node A, I'm going to encounter V1 next. I see a positive sign first. I'm going to treat V1 as a positive voltage difference. Now I'm going to go down to element 4. At V4, I see a negative sign first. I'm going to treat that as a negative voltage difference. V6, I see a negative sign first. That's going to be a negative voltage difference. Those have to sum up to 0. This loop here, I normally loop clockwise, but I guess just to show that it doesn't matter, I'll loop counterclockwise this time. As long as I'm consistent, as long as I indicate what direction I'm going, it doesn't matter. So loop 2 is here. Let's start out at node E. I'm going from node E counterclockwise. I see V5 first. I've got a negative sign there. V2 comes next. I see its positive voltage node first. So that is a positive voltage difference. V4, I see the negative sign on its voltage polarity first. I will treat that as a negative voltage difference. Those sum up to 0. My final loop is all the way around the outer perimeter. Doesn't matter where I start on this loop as long as I'm consistent about the direction that I go and as long as I end up at the same point I started at. Let me start at point A. At A, I see the positive node of V1 first. That's going to be a positive voltage difference. I see the negative node of V2 first. That's a negative voltage difference. I see the positive node of V5 first. That's a positive voltage difference. I see the negative voltage node of V6 first. That's a minus sign. And I see a negative V3. Those all have to sum up to 0. I've come back to my starting point. If I add up all these voltage differences, I have to get to the same voltage at node A that I started out with. Okay, now let's talk about using KVL and KCL to perform an overall circuit analysis. When we're analyzing a circuit, typically what we want is to determine voltages and currents for one or more circuit elements. If we want to determine voltages and currents in all elements, we can always follow this procedure. We can write a voltage-current relationship for every single element. For our case, for resistors, it's going to be Ohm's law. We'll have some different voltage-current relationships later when we get to capacitors and inductors. We can apply KVL around all but one of the loops in the circuit. Then if we apply KCL at all but one node in the circuit, what we will end up with are a set of n equations in n unknowns, the n unknowns being the voltages and currents in the circuit elements. Let's do a quick example. I want to analyze this circuit here to determine the power generated by the source and the power dissipated by each of these resistors. Okay, so what we're ultimately going to need to do is find voltages and or currents across each of the resistors, find the current through the source, determine powers for each of those, and then I want to use conservation of energy, which we mentioned we were going to review a little bit earlier on. Now we're going to actually use it again, use conservation of energy to make sure that everything works out. So give that a try and come back and watch me do it. Okay, first thing I need to do is decide my voltage polarities and my current directions for my two passive elements. I'm going to assume that the 1 ohm resistor has a voltage V1 where the positive voltage is at the left, and I'm going to assume that the 2 ohm resistor has a voltage V2 where the higher voltage is at the upper node. If this is my voltage polarity, I have to assume that I1 is positive in this direction, and I also assume that I2 is positive in this direction. Now I've got my passive sign convention all set up and everything's hunky-dory. Always do this before you start applying KVL and KCL. It'll save you a lot of grief and a lot of time in the long run. Okay, now I can apply, let's apply KCL here at node A. KCL tells me that the sum of the currents going into the node has to be equal to the sum of the currents going out of the node. I have one current going into the node, I1. I have one current coming out of the node, I2. So KCL just tells me that I1 is equal to I2. If you want to use KCL in its other incarnation, where you add up all the currents at a node and set that equal to 0, you just have to decide what you mean by positive currents. If I want positive current to be going into the node, so alternately, if I1 is treated as positive, I1 plus I2 will have to be negative. I1 minus I2 is equal to 0. I get the same result regardless of what application of KCL I use. I only have one loop. Applying KVL around this loop, and let me start here and start adding up voltage differences around this loop. So I hit the source first, so I have a minus 2 volts because I see the negative voltage terminal first. V1 is assumed to be positive here, so I add V1. V2 is assumed to be positive. I see the positive polarity node first, so this is plus V2. Those guys sum to 0. So at the moment, I started out by writing one equation with two unknowns. Okay, I can't solve one equation and two unknowns, so I wrote another equation which also has two unknowns. Unfortunately, they are two different unknowns than this one, so we are currently looking at two equations and four unknowns. Things are getting bad for us. However, what we haven't done yet is invoked Ohm's law for both of these resistors. That will give us the two other equations that we need. Okay, I think this is where I ended up on the last slide. I had two equations and four unknowns. I said that I now need to use Ohm's law to write two more equations. So Ohm's law tells me that V1 is equal to 1 ohm times I1. So V1 is equal to I1. And V2 is equal to 2 ohms times I2. So V2 is equal to 2I2. Since I1 is equal to I2, this guy here is equal to 2I1. Substituting this in for V1 and this in for V2 gives me one equation and one unknown. So minus 2 plus I1 plus 2I1 is equal to 0. So 3I1 is equal to 2, so I1 is 2/3 of an amp. Okay, so now the power dissipated by the 1 ohm resistor is just the resistance, 1 ohm, times I squared, 4/9. So this is 4/9 of a watt. The power dissipated by the 2 ohm resistor is 2 ohms, resistance times I squared. I2 is equal to 1. So this is 2 ohms times 4/9 is 8/9 watts. Now I need to determine the power dissipated or generated by this 2-volt source. Now at this point I want to make a point of something. I did KCL here at node A. That ultimately ended up giving me 4 equations and 4 unknowns. I can apply KCL up here, except up until I've solved for these unknowns, it doesn't do me any good. If I apply KCL here, all I get is that the current coming out of this voltage source is equal to I1. So, for example, I2 volts is equal to I1. Yes, I've added another equation, but I've also added another unknown. I haven't gotten ahead of the game in any way whatsoever. In general, applying KCL at either the inlet or outlet of a voltage source is not going to help you because you know nothing about the current through a voltage source. Remember, an ideal voltage source can have any current that it needs to going through it. However, to get this power from this guy, we need to determine the current. Now KCL at node B helps us out. So KCL at B says that the current through the 2-volt source is equal to I1, which is 2/3 of an amp. So the power of the 2-volt source is equal to 2 volts. Current is actually leaving the positive voltage node. I treat this as a minus 2/3 amp, so this is minus 4/3 of a watt. So this is actually generating power, which is a darn good thing because resistors can only absorb power. I need to give them power from somewhere. Checking with conservation of energy. I have 4/9 watts plus 8/9 watts is equal to, well, plus minus 4/3 watts. That's equal to, if I multiply through by 9, I get 4 plus 8 is 12. Minus 12 is equal to 0. It looks like I'm okay. Another example. For this circuit, I want to write the necessary equations that I can use to determine the current through the 2 ohm resistor. I'm going to end up with a fair number of equations here. I don't want to solve them, but I do want to write the equations. So, labeling the voltages and the currents in my passive elements, let me call this V1, in which case I1 has to be positive this way. Let me call this guy V2, in which case I2 has to be going into the positive node of V2. Call this guy V3, in which case I3 has to be going into the positive node of V3. Now I know what I mean by positive numbers everywhere. I can continue on with my analysis now, and things will ultimately make sense to me. Let's apply KCL. As I said before, KCL applied here is not going to help me much because it will introduce another unknown, which is the current through the voltage source. So let's do KCL at this node. Okay, let's call this node A and do KCL at A. So, sum of the currents entering the node is equal to the sum of the currents leaving the node. So I1 is going into the node. It is assumed to be going into the node. We don't know for sure that it is doing that yet. I2 and I3 are assumed to be going out of the node. So if you want to sum them up and set them equal to 0, you're going to have I1 minus I2 minus I3 is equal to 0 if you assume that currents going into the node are positive. Let me do KVL around loop 1, which is going to go through the 10-volt source V1 and V2. So KVL 1, I'm going to start at the lower left-hand corner, work my array around, and come back to the lower left-hand corner. I see the negative terminal of the 10-volt source first, so I get a minus 10 volts. I see the positive terminal of V1 first, so I get a plus V1. I see the positive terminal of V2 first, and that becomes a positive contribution. Those guys sum up to 0. So far I have one equation with 3 unknowns. I've added another equation. I have 2 more unknowns. I so far have 2 equations and 5 unknowns. Let's do another loop, maybe around the entire perimeter of the whole thing. Let me loop around here. So KVL2, I'm going to start at the lower left-hand corner again because it worked so well for me last time. I get a minus 10 volts plus V1 plus V3 is equal to 0. Then I'm back to my starting point. Okay, I've now added another equation and another unknown. I'm now up to 1, 2, 3, 4, 5, 6 unknowns and 3 equations. I'm actually in good shape at this point because I can get another 3 equations from Ohm's law for the 3 passive circuit elements. So by applying Ohm's law, I can claim that V1 is equal to 2 ohms times I1. V2 is equal to 4 ohms times I2, and V3 is 4 ohms times I3. I now have 6 equations and 6 unknowns. I can go away and solve those. When I solve them, then I will know what V1, V2, and V3 are. I will also know what I1, I2, and I3 are. I want to find the current through the 2 ohm resistor. I just need to pick I1 out of the resulting unknowns. I want to do the same example again. Okay, last time I just started picking nodes and loops, and it may have looked somewhat random. I was just writing circuit equations until I got 6 equations and 6 unknowns. Guess what? It was random. I didn't need to pick those particular equations. I could have generated different equations by picking different loops or different nodes. So for example, I'm going to use my same sign convention, V1, I1, V2, I2, V3, and I3. Oh, I still like this loop. I'm still going to do loop 1. It'll give me the same result I got before. Negative 10 volts plus V1 plus V2 is equal to 0. Well, how about if I loop around this little guy here? So loop 2. KVL, loop 2. Now, I guess I'll go ahead and start down here. I see the negative terminal of V2 first, negative V2. I see the positive terminal of V3 first, plus V3 is equal to 0. I now have 2 equations in the 3 unknown voltages. I did KCL up here last time. I don't really want to do KCL down here for the reason that I'll have to get the current through this voltage source involved. So if I do KCL down at this node, I'll end up with a current that I don't know what it is going through this guy, so I'll end up having to write another equation anyway. I'll end up having to loop through here or do KCL up here. I might as well just go ahead and do my same KCL equation that I did before. So KCL, node A, that'll give me I1 is equal to I2 plus I3. Okay, and then I can apply Ohm's law to get V1 is equal to 2I1, V2 is equal to 4I2, and V3 is equal to 4I3. I still ended up with 6 equations and 6 unknowns. I can solve those to get the same solution that I got before. Okay, the circuit analysis approach that we've been using above, in which we define n unknowns, which are the voltages and currents of all of the passive circuit elements, and then writing n equations in those unknowns, has an official name. It's called the exhaustive method. After you're done with this, you know everything about that circuit that you need to know. However, sometimes it's not necessary to go through every single one of these steps. If we're interested in some subset of the circuit parameters, maybe a particular voltage, a particular current, the power dissipation in a particular element, we may be able to get by with writing and solving fewer equations. So in many, many cases, sitting there and staring at the circuit for a few minutes and deciding what to do that will make your solution efficient is time that is extremely well spent. For example, this problem, I want to find the current through the 2 ohm resistor, I want to find the current through the 1 ohm resistor, and I want to find the power generated or absorbed by the source. Take a quick look at this, see how few equations you can get this down to in order to solve for those desired unknowns. When you come back, I'll show you what my plan is. Okay, you don't want to skip the step of applying your passive sign convention. If V1 is this direction, I1 has to be this direction. If V2 is this direction, I2 has to be this direction. Okay. We want to find the current through I1. Let's see, if we do KCL here, we'll get a current that we don't know what it is. We'll have one equation with 3 unknowns. That doesn't look really profitable. Let me try a loop through here. So loop 1. KVL for loop 1. If I start at the lower left-hand corner, as is my habit, I hit the negative terminal of the 4-volt source first, so I ended up with a negative 4 volts. Then I'll hit the positive terminal of V1 first. That'll become a positive term. That's all I have. So V1 is just 4 volts. Need a capital V for volts. Well, if it's a resistor and I know the voltage, I can just use Ohm's law to find the current. So I is equal to V over R. So I1 is 4 volts over 1 ohm. I1 is just 4 amps. Now that we've done that here, we kind of see that we can do the same trick for this other one by looping through the source and through that single resistor. Call this loop 2. So KVL around loop 2, I have a negative 4 volts from the source and a positive V2. So that sums to 0. So V2 is also 4 volts. I2 is this voltage over this resistance. So that's V2 over 2 ohms. So I2 is 2 amps. So we've got A and B done. We really just had to write 1 KVL for each one of these and then invoke Ohm's law. In order to find the power absorbed or generated by this source, we need the current through the source. So I, 4 volts, I'm going to assume it's positive that direction. I can find that current very easily by doing KCL at this node. So KCL tells me that if I assume that the currents going into the node are equal to the sum of the currents coming out of the node, I get I, 4 volts, is equal to I1 plus I2. So the current through the 4-volt source is 4 plus 2, which is 6 amps. If the current through the source is 6 amps, The power dissipated or generated by the source is going to be 4 times 6. I got a positive number here, so current is leaving the positive voltage node. That means that the power is being generated, so it's a negative number. So the power of the 4-volt source is just 6 amps times minus 4 volts. So that's a minus 24 watts. It is generating power. And it's okay with me if you want to list this as a negative 24 watts, or if you want to say that this is a positive 24 watts generated. Either of those will tell me what this guy is doing. This concludes lecture 3. When I come back next time, we'll do some more examples of KVL and KCL. KVL and KCL are going to be extremely important to us. They're our main analysis tools for the rest of the semester. Once we've done that, what we'll do is start trying to simplify our analysis approaches. We'll notice that certain combinations of circuit elements can be simplified, and that can make our life a lot easier. We'll start doing circuit reduction techniques.